Look at the world around us. We build these towering skyscrapers, massive ships, intricate offshore pipelines. Yet all of these engineering marvels are under constant attack by a quiet, unseen force that literally never sleeps. Welcome to this explainer. Today we're diving into the dense, high-stakes science of corrosion and protection. We're going to break down exactly how humanity fights this relentless billion-dollar war against an invisible electrochemical enemy. It's kind of funny to think about it at first, right? The source material actually drops this wonderfully whimsical poem by T.R.B. Watson. He jokes about mighty ships rapidly becoming oxide, and how, when the wind is salt and gusty, things are getting awful rusty. It's a lighthearted, deeply ironic way to introduce what is, in reality, an incredibly destructive problem.
But let me tell you, the stakes are absolutely no joke. This invisible antagonist literally evaporates an estimated 3 to 4% of the gross national product in industrialized countries. I mean, think about that massive scale for a second. That is a huge amount of capital, literally turning our infrastructure to dust and demanding multi-billion-dollar maintenance budgets year after year. It's a constant drain on resources that we often take completely for granted until something breaks.
To ground this in the real world, just look at some of the casualties. At the DuPont Company, over a 2-year period, a shocking 57% of all recorded material failures were corrosion-based, compared to just 43% for mechanical failures. And the greater Ekofisk offshore oil platform out in the North Sea, finding this enemy cost them 20 million British pounds in just a single year between 1981 and 1982. Statoil tells a really similar story, reporting that about half of their offshore material failures are directly tied to corrosion and corrosion fatigue.
So, to understand how we actually fight back, we need to shift our focus from that massive global scale right down to the microscopic level. Let's get into Section 1, the battlefield of wet corrosion.
First things first, we've got to clearly define our enemy here. Wet corrosion is fundamentally an electrochemical attack on a metal, but here's the absolute critical part. This attack can only happen when a conducting liquid is present to act as the combat zone. We call that an electrolyte, so think seawater, fresh water, or even just condensation in the atmosphere. Without that liquid there to close the electrical circuit, this specific type of corrosion simply cannot happen. No way.
Now zooming in to the microscopic level, let's look at the actual mechanics of the attack, an electrochemical cell. At the anode area, the metal actually breaks down. It dissolves, sending positive metal ions right into the liquid. And at the exact same time, it releases electrons. Those electrons then travel through the metal over to the cathode area, where they're consumed by a reaction with oxygen and water, creating hydroxide ions. Basically, it's a complete electrical circuit running constantly and using the metal itself as its fuel.
So what's the crucial point here? It's what happens next. When those dissolved positive metal ions meet those negative hydroxide ions in the liquid, they combine and deposit right on the surface. If we're talking about iron with plenty of oxygen around, they form iron hydroxide. You know the stuff. It's the ordinary flaky brown rust on our cars and bridges. But if oxygen is heavily restricted, you instead get a totally different chemical compound, F3O4, which shows up as black or green rust.
All of this raises a pretty massive question, though. Why does the metal want to destroy itself in the first place? Well, to find out, we have to look at the underlying physics in Section 2 Thermodynamics, Nature's Driving Force.
To really wrap our heads around the concept of free enthalpy, just think of a stone resting at the top of a hill. Gravity spontaneously forces that stone to roll down the cliff, right? It wants to reach a lower energy state at the bottom. Well, thermodynamics works exactly the same way for metals. The refined metals we use to build our world are in an artificially high energy state. Nature naturally drives them to corrode, essentially rolling them down the thermodynamic hill to reach a lower, much more stable state of free enthalpy. Let's look at the 3 thermodynamic rules of engagement governed by what scientists call free enthalpy, or simply G. When G is negative, the reaction is spontaneous. The system releases energy, and nature itself relentlessly drives the corrosion attack without needing any extra push. If G is exactly 0, we have a balanced stalemate. And if G is positive, well, the reaction won't happen naturally at all. Energy would have to be externally supplied. The bad news? In the case of most metals in wet environments, G is stubbornly negative.
And this is exactly where the abstract physics meets real-world engineering. Scientists measure this thermodynamic driving force as a reversible cell voltage.
That means the fundamental thermodynamic urge for a metal to dissolve can actually be read right on a voltmeter. By measuring this potential difference between an anode and cathode, engineers can definitively prove whether a corrosive attack is theoretically possible in any given environment. Now, knowing the enemy's motive, that negative free enthalpy, is super important. Thermodynamics tells us if an attack can happen, but we need kinetics to tell us how fast it's going to happen. Which brings us to Section 3, measuring the invisible damage. Engineers use conversion factors derived from Faraday's equations to actually track this damage. The massive takeaway here is that corrosion is, at its absolute core, just an electrical current. An electrical corrosion current density of just 1 microampere per square centimeter translates to roughly 0.01 millimeters of solid metal lost every single year. You can directly translate the electrical current of the corrosion cell into physical, structural loss.
To put that into a real-world perspective, imagine an unprotected piece of structural steel placed in seawater. It will naturally run a corrosion current of 10 to 15 microamperes per square centimeter. So that means it's going to lose about 1/10 of a millimeter of its thickness annually. I know, it sounds super small, right? But over 10 or 20 years, that is a slow, invisible, and completely relentless march toward catastrophic mechanical failure.
So, if the stone always wants to roll down the hill, how do we possibly defend our bridges, our ships, and our pipelines? Let's get into Section 4, Strategies for Prevention. Engineers have basically established 5 main lines of defense to fight back. First up, choosing tougher materials that form natural protective passive oxide films, like stainless steel. Second, changing the environment itself, maybe chemically removing oxygen or adding inhibitors. Third is clever design, literally shaping structures so water can't pool and crevices are completely avoided. Fourth, altering the electrical potential using what's called cathodic protection. Think of attaching a sacrificial chunk of zinc to a steel hull so the zinc corrodes instead of the ship. And finally, the most visible method, applying protective coatings like paint to form a physical barrier.
Every single one of these defensive strategies ultimately aims to do one simple thing. If you think back to that microscopic cell we talked about earlier, the goal is always to interrupt that electrochemical circuit. Whether it's by starving the reaction of oxygen, trapping the electrons, or placing a physical paint barrier to block the electrolyte entirely, we survive by breaking this circuit.
Which brings us to a rather profound final thought for this explainer. We've seen that this destructive force isn't just an accident, right? It's hardwired into the fundamental thermodynamic laws of our universe. Metals desperately want to return to their natural state. So, is this a war we can ever permanently win? Or is human engineering destined to be an endless, billion-dollar battle for maintenance against the inevitable forces of nature? It really makes you look at a rusty bridge or a painted ship hull in a completely different light.